Hello everybody, I'm Guillaume and today I'm going to present you my paper Adversarial Counterfactual Visual Explanations. In this paper we studied the ongoing branch of explainable AI, counterfactual explanations. These explanations search to solve the question, what does X have to change in order to alter the prediction from Y to Y prime? Yet, these changes should be human understandable to be able to study them. Adversarial attacks seek the same objective that counterfactual explanations, to fool the classifier. But the produced noise of adversarial attacks are imperceptible, while counterfactual explanations want to input perceptual changes. But having imperceptible noises is understandable, since we cannot study them visually. Nonetheless, previous literature have shown that robust models can be used to input semantic changes. So, there are objectives for counterfactual explanations to follow. The first one is to flip the classifier's decision. Then, to create sparse and proximal changes. And finally, the final instance must be perceptually realistic. Hence, in this paper we solve the question, how may we use adversarial attacks to generate semantic changes for any model regardless of its root specification. So, our contributions are as follows. Our technical contribution is a counterfactual explanation method based on adversarial attacks. Performance-wise, we outperform prior state-of-the-art in multiple measures and multiple datasets. We extended previous evaluation protocols to generate a set of images. And finally, by analyzing our explanations, we were able to produce actionable changes in real life to flip the target classifier. Following with the methodology, we seek to robustify the model without changing its weights. This model that we're going to add at the beginning of the classifier should filter high frequency signals without changing the original prediction. And the final product must lie in the data manifold, such as in the example. We notice that diffusion models achieve this property if used properly. The core idea is then use adversarial attacks, but instead of generating the gradient of the classifier directly, we compute them through the DDPM classifier module. Therefore, A's algorithm is as follows. First, we add some noise to the input image that we want to explain, and then apply the filtering process. We use this filtered image to compute the loss and propagate the gradients into the first image. Finally, we use the gradients to update the adversarial attack on the original instance, and then repeat until generating the counterfactual explanation. By observing the difference between the attack image and its filtered version, we observe that the filtering image modifies unwanted regions, such as the hair, while the attack is localized. Hence, we adapt in painting strategies to modify only the regions of interest. Nevertheless, in painting uses user inputs to select where to modify the images. A simple trick is to use the difference between the attacked image, so the one that is not filtered, and the original input as the mask, and use it as a refining process. By leveraging this mask and the repainting method, we can include the original image pixels that did not change in the final product. In contrast to previous state-of-the-art, it generates better and more realistic explanations. For instance, DIMES produces out-of-distribution noises as well as changing the ice color, while ours input realistic modifications. For objects, such as hats, we do not modify them as much, and add smaller changes in the image. An advantage of ACE is that we produce a localization mask showing where we input the changes, and the counterfactual show what we change. By studying our counterfactual explanations, we were able to find the inductive biases learned by the classifier. For instance, a young old classifier with a cipher that wrinkles flip the classifier decision. So by performing these changes in real life, we were able to flip the prediction. Similarly, persons with naturally high cheekbones are susceptible to be classified as smiling. And we can further enhance this natural adversarial example by adding some red makeup in the cheeks. Finally, we extended the evaluation metrics to assess general explanation in images. Performance-wise, ACE outperforms previous state-of-the-art in multiple metrics. Please refer to our paper for more details. In conclusion, we propose ACE to generate counterfactual explanations leveraging adversarial attacks. ACE is a method that provides realistic counterfactual explanations in addition to localization masks. Furthermore, ACE is able to decipher biases learned by the classifiers, such that we can learn these inputs and adding them in real life to flip the prediction, something never done before in the counterfactual explanation community. Feel free to ask me any question, and please visit our webpage and GitHub code. Thank you very much.